Thanks, everyone. So my name is Krishna. I'm the founder of Fiddler Labs. We're a startup in Mountain View. We're working on this explainable AI platform for enterprise. Previously, I was an engineering lead at Facebook, Pinterest, and Twitter, working on machine learning and data platforms. So the topic I'm going to talk today is obviously very relevant in today's age. Here's the agenda. So we're going to cover like why we are talking about what we are talking, some of the challenges we have been observing around model explainability, and a proposal to think about fairness. This is obviously a very debated topic. I'd love to hear questions about it. And then what we are doing to operationalize these concepts as a product. So to start with, this is something that everyone knows, right? So we're kind of seeing this third revolution in the last 20 years. It started with the internet revolution, and then like mobile revolution. Now everyone is trying to build AI-first apps, and in the future maybe we will have mostly AI-only applications. And this is happening across industries. Pretty much every company that's deploying AI sees huge improvements in their operational efficiency, personalizing their products to the end user, increasing revenue growth. But there are concerns about machine learning, right? So if you don't do it right, there are heavy penalties to pay. If you are a regulated industry, for example, JP Morgan paid up a lawsuit for sort of $55 million for like discrimination in their mortgage decisions, and you have seen all the other news around like tech companies producing biased AI products. So the reason why this happens today is increasingly machine learning is becoming a black box. So as models become more and more complex, they're very hard to reason about, even by the practitioner who's building the models. And when you deploy them, you really don't know what they're doing, why they're doing. When can you trust them? And what are the cases where machine learning models can fail? So here's an example, right? So today, if you go to any bank and ask for a credit line increase, this is a fully automated request. Essentially, you may go for like, hey, I have a credit card worth $5,000. I want to increase it. Most banks actually automated using a machine learning model that basically returns prediction, and based on that, a decision is made. And there is no visibility into why this decision was made, why not, like how could the end user make a better case in the future. And similarly, when you're building machine learning models, these are models being trained on the data, and as a society, we are not yet a perfectly equitable society, and the data drawn from the society will have bias. So for example, let us say I'm building a face recognition classifier to identify who will be a nurse. I mean, this is a hypothetical example, no one should build it, but let's say if I'm building it, then I will have a lot more positive examples from women being like nurses than men being nurses. So a classifier will automatically be biased against men. And similarly, to address some of these things, governments are introducing regulations. So you probably have heard of GDPR. So the Article 22 of GDPR states that if a company is actually introducing a system that makes automated decisions, typically these automated decisions are made using machine learning, then consumers have the right to demand an explanation. And similarly, these kind of GDPR-like laws are being introduced in the United States as well. There's California Consumer Privacy Act that's going to be in vogue from Jan 1st, 2020, that restricts how much personal data that companies can use for analytics and machine learning, and similar laws are being introduced in other states. So in summary, if anyone is actually thinking about deploying AI, has already deployed AI, these are some of the business risks they face today, right? So like, how do we deal with unfairness? How do we deal with compliance? How do we deal with black box models? And how do we make sure that we are respecting user privacy? Now, if you step back, how did we get here in the first place, right? So why are companies facing these problems? Why are we in this situation today? So just a brief primer about machine learning. I mean, basically, what happens in machine learning is you try to model what happened in the past to predict the future. So for example, let's say I'm trying to build a fraud detection classifier. I look at all the historical transaction where I know the ground truth of which transaction is fraudulent and which transaction is legitimate. And using that data, I apply a machine learning process to build a classifier that I can then apply on new transactions so that I can classify fraud predictions. Now, when we do this, we obviously want the best model performance. We want as fewer errors as possible, so we try to optimize for like performance metrics such as area under the curve, precision, recall, you name it. But increasingly today, we also want human interpretability. So we're not just satisfied with performance. We want like, oh, I want to know why the model is making that decision. And this is why it becomes challenging. So imagine I'm actually building a fraud detection classifier using very simple, like 2 variables. Let's say I know the distance from home of a person where the transaction was made and the amount of transaction. Let's say I only have 2 variables to decide. Now, I can construct a very simple linear classifier that can classify between the positive examples, positive meaning the fraudulent transactions, and the negative examples, the not fraud transactions. And so this is also easy to explain. So I can explain to someone, hey, this classifier works this way. If the transaction was done at a longer distance from home, or the transaction amount is quite large, then the classifier actually classifies it as fraudulent. That's pretty simple. Let's make it a little bit more complicated. Let's say the distribution of the data is like this. I could still build a simple to reason about classifier, a decision tree in this case, where I could basically say if the distance from the home is so and so and the transaction amount is greater than so and so, then I would classify this transaction as fraud. Everything else is not fraud. Again, simple to reason about, pretty effective. However, in real world data, it's not like 2 attributes, it's not a few transactions. You have millions of transactions, it's hundreds of thousands of variables that you may want to model against. It's very high dimensional data and it's very complex. So global interpretability, global understanding of the model, of how the model in its entirety behaves will become challenging. As you try to model those data, you'll have to build nonlinear models. Right? So what we end up doing is basically estimating estimating the predictions locally, basically. So why this can be possible is, even for a nonlinear model, for a given prediction point, for a given data point, you can try to construct a local approximation, a surrogate model, to try to see why the prediction was like that, was like whatever that number is. And there are papers being published in this area, Lime being the most popular algorithm out there. And this is how a lot of data scientists today do explanations. So they either use Lime or SHAP in a Jupyter notebook to sort of like see what's going on with their data set. Let's say they build a model. How does the model actually perform and generate these explanations, right? And using those things, they can get some insights. The question is that good enough, right? Like, is this technique or is this like a good enough practice to go with? Now, like, what do we want from explanations, right? Like, so when we are trying to build explainable AI, what exactly are we trying to get at? One of the main things is we want trustworthiness, right? We want to know, will the model like perform the same way as it was performing when I was training, right? Will the model make better decisions than a human being? At a base minimum, if you make like human decisions being like the bar, and will the model actually make better decisions than human? And you also want to identify causality. You just don't want to know how the model is working, like for example, what features are contributing to the model to make that decision, but you also want to know why, right? Oftentimes, is it because there is corruption in data, there is corruption in features that you are actually getting to actually make this prediction. So the causality of actually understanding why the prediction is whatever that is very important. And you also want these explanations to be transferable, right? So oftentimes, your train and test setups are very different from real world. Your training data distribution and your real world data distribution may differ because your models are subject to externality. There could be seasonal effects or user behavior changes. And the real world data is often noisy. And most often than not, you use model predictions to actually not directly use the model predictions to make automated decisions, but there's generally a human in the loop. So you are using these model predictions to aid human decisions. So in this case, you're wanting explainability to actually supply more information. So don't just tell me the credit risk prediction for a certain person is 0.3, but also give me reasons why the model is actually predicting that way, right? So explainability, in summary, what you want from explainability is like you want to be able to trust the models that you're building. You want causality when you actually deploy those models, so actually you know why they're performing, how they're performing. And you want transferability so that you can actually explain things, how they're going, what's going on in the real world, and you want more information. So how would such a platform look like? That's what I'm going to demonstrate today. And before that, let's look into fairness, right? And so there's the other aspect of machine learning that's highly debated today is machine learning classifiers can be unfair. And so how can machine learning classifiers be unfair? Now here is an example where this is a very well-known case study that many people might have looked at, where there's this face recognition algorithm was applied across various genders and demographics, and the accuracy of the models on darker females was quite low compared to the rest of the population. And so this is where people will complain hey, this model is actually being unfair to a certain population. Now, how would you identify this? This happens generally because maybe you don't have enough examples from that population. But how would you identify this thing while you're building models? So here's a framework to think about it, right? So if you think about how would unfairness can actually enter into your machine learning, you can kind of decompose it into three parts. So this unfairness could be because of model bias. Unfairness could be because models variance is actually high or low for certain populations. Unfairness could be because you have a lot of noise for certain population, and you may not have good features or discriminating features for those populations. So let's look at each of these each individually. So let's say I'm trying to build a regression model for some machine learning task, and I have two populations, male and female, and they are distributed like this, right? And if I try to build a very naive regression model, it will be having a high model bias for the females, in this case, the orange dots, because they have a very different distribution, right? The female data distribution is quadratic in this case, where the linear male data distribution is linear. So if this is what is happening, maybe you need to think about if your data distribution for different demographics is very different, and you've observed this in your training data, this is probably a case to think about building different models, right? Like building different models or changing the model class for the different groups. Now, oftentimes you don't have tools to actually make this visible. And another example is where let's say if your data distribution is like this, where you have again, like female being orange and male being green, and you have high model variance for males. So basically, if you try to fit a line, the average distance from the green dots to the line is actually much larger, right? And so in this case, basically, this can happen when you don't have enough examples. So this can happen in that nurse face recognition example, right? So when you don't have enough examples, you may try to fit a model that's not good enough for a certain distribution. In this case, the takeaway could be you have to sort of collect more training examples for those underserved classes. Another case could be where you may have noise, right? So let's say your features are not discriminating enough for a certain population. In this case, let's say the green dots are all over the place. They're not following a certain pattern, right? And there's no way to actually fit a model that works for them, right? So in this case, your features that you may be collecting for that population are not discriminating enough or don't have enough information that can be captured, in which case you may have to sort of think about you need to sort of collect better features for those noisy classes. But you need better tools to actually look into the data to actually identify these cases and see what you need to do. So in summary, these are some of the reasons how you can actually decompose bias. In cases where there is high model bias for certain groups, maybe you need to experiment with model complexity. So either you need to separate your models for each different groups, or you increase the complexity of the model for the overall data. Or in cases where you may have high variance, you need to collect more training data for certain classes. And in cases where there is more noise because you don't have good features, you may have to build better features. And so this seems obvious when you actually look at it, but the reason why this is difficult is you need like visibility into this training process, and that's what we are building at Fiddler. So that's what that's kind of the rest of the slides talk about. How can we operationalize these concepts? Before I go into some of the sort of demo slides, basically think about this, right? So essentially when you're building models, you are trying to optimize for the performance of the model, as we talked about, but at the same time, there's like you are trying to keep the model fair, and that's a philosophical decision. So it's an organization or company-wide decision. It's not an algorithmic decision. And then you want transparency into your machine learning models, and you want to respect user privacy. They're all having trade-offs with each other. For example, let's say I want to build an ultimate, absolutely fair model. I cannot do it without knowing the private information of the user. I need to know the protected class, like the gender, your race, or the school you went to be actually be able to build the most perfect, the fairest of the models, right? And similarly, there's a trade-off between performance and fairness, right? So if I have to be absolutely performant, I may have to sacrifice fairness, and vice versa in certain cases. And especially, and if again for transparency, if you're trying to build the best model and you're trying to build a multi-layer neural network, it would be very difficult to interpret. So that means you're also sacrificing transparency. So you need to pay attention to these trade-offs as you're building your machine learning models. And so that's kind of what we are trying to build here with Fiddler, where we are trying to build an explainable AI engine that provides these insights to the modeler, to the operations person that is actually deploying these models and serving customers, to the business analyst that is analyzing the machine learning-based products. So we help companies build interpretable models, manage risk around the models, govern sort of like the model building process, can provide continuous explanations throughout, like even after deployment, and insights into fairness and causality of why it's happening, what's happening in production. So what would be some of the use cases for when such a system exists, right? So if you have explainable AI, you can actually audit your machine learning models. Before you deploy them, you can audit them for bias and transparency. If a customer complains to you, let's say you are a lending firm, and someone asks you why was my loan rejected, your customer operations team can actually answer them in a proper way. You can conduct performance analysis. You can compare two different models along various axes and do performance analysis. You can analyze causality. So, for example, you've suddenly seen predictions are going haywire for certain demographic or for a certain location. You can understand what's going on, why it's going on. And you can apply governance so that you can have like multiple stakeholders involved throughout your machine learning process. So here is kind of like a screenshot of how auditing black box models for bias looks like. Imagine like that fraud detection model that we built. Let's say in this case, the fraud detection was for a user, whether a user was signing up or something, and so you basically wanted to detect the fraud. And so this is again like it's not a real example, but like what could it look like? So in this case, what you're seeing is basically features of that user on the left-hand side: the age, FICO score, salary, credit requested, and the values, and then the amount of impact of the feature on the model prediction. So here basically you're trying to figure out why did the fraud detection model classify this user as 0.3. Maybe it's like basically classifying as like a low risk user or whatnot. And so there are maybe some features that are negatively affecting the model performance, like the marital status of the user or gender. Is this something like you should be using? Is this like something that, I mean, this is perfect. I mean, again, there's no like hard and fast rules, right? Like, as I said, there's no hard and fast rule. Should you be using private data? Should you not be using private data? In some cases, you may have to use private and protected data to be actually fair. So, but this gives you visibility into whether you actually need those protected variables and knowing how much they're contributing to the model performance. In this is a much more advanced use case where, let's say, you're building a deep neural net, and you want to figure out how many layers you need to add at design time, and you want to know the discriminating capability of each embedding, right? And so in this case, what you're seeing is a neural net that is trying to classify a piece of text into 5 categories: politics, science, entertainment, shopping, and sport. And you are basically noticing the neurons that are getting activated at each layer, right? And at the same time, you're seeing the kind of a 2D plot of the discriminating capability of how good like each embedding, like let's say you took the embedding of like the final layer, how good in terms of it, how good of a discriminator it is for the 5 classes. So as you can see, the last layer is much more discriminating. It separates the 5 classes much more cleanly than the last but 1 layer and the last minus 1 layer. And you can also use explainability to actually power end users with contextual explanations, right? So here's an example where like a company like Facebook would use a feature like, why am I seeing this ad, right? So if you go to Facebook, this is actually my feed, and I was shown this ad a few days ago. Facebook noticed that I was probably coming to Strata. Now it's advertising me to come to the New York conference, right? And so here, when I click on it, it gives me an explanation. This is not a very extremely convincing explanation, but this is where like how you could actually generate these contextual explanations and show it to the end user. And even with governance, what you can do is, because when you are building machine learning models, you're not building them in isolation. Oftentimes you build them like you have the related models, they have related features, they have related metrics, they may have some different policy exceptions. You need a workflow that actually can connect your model builder to the operator and the internal auditor in one place. And so you'd get like a 360-degree model governance with Fiddler. Yeah, so basically what we offer is like once you use the platform, then you can generate better trust and retain your customers and apply AI governance and like be kind of compliant with regulations and have your data scientists be more effective and have operations teams get greater visibility into AI. So that's kind of end of my talk. I'm happy to take questions. We're building, as I said, we're building a general purpose explainable AI engine. The product can be plugged into any ML platform, whatever ML platform that you'll be using. Here's the team. We're a startup in Mountain View. So if you have any questions, you can also reach me offline, but I'm happy to take questions here.
Sorry, your platform, the explainable AI, is both for building models from scratch and explain them, or is it only for explaining them?
Today, the product that we have is for explaining models. So, for example, you could be building models using using your own open source software like TensorFlow, Scikit-learn, or any customized ML platform or a third party. We can plug into that platform basically. Yeah.
I have a question.
Sure.
So are you suggesting to undersample the data, oversample the data?
Sorry. Okay, yeah, sorry. Yeah.
So because your model is biased, because it was fed with the biased information, right? And maybe the class representation was not what it should be to be a biased, non-biased kind of model. So whether your tool helps on that aspect of feeding undersampled or oversampled or kind of augmented data. So what are suggestions on that side?
Yeah, so we basically provide insights into what's going on with your model, right? So with this, you can actually see, let's say, your model, how is the model performing across multiple like gender classes or multiple like zip codes or multiple sort of whatever segment that you want to bisect it. That way you can see if the model performance is weaker on a certain class, let's say certain gender, certain race, or certain skin tone, you can go and see what's going on. Is it due to the lack of training examples? Is it due to lack of discriminating features? Or is it because like you have to fit a better model, right? Like it's the model complexity is not sufficient to capture the data, right? So we provide the visibility, but it's up to the modeler to actually make those decisions, go back to the drawing board and figure out what they need to do.
Sorry to make you run around. So without trying to dig into your secret sauce too much, is this sort of like Lime or something where you're basically querying the black box and building a model based on the responses that you're getting back in an interpretable modeling format?
Yeah, that's a great question. So we are using SHAP, the Shapley algorithm, which is actually which we found in practice to be much more scalable and much more stable. So we've tested Shape. We have actually produced a blog post recently. I can send it over to you, or you can just go to medium.com/Fiddler Labs, where we have written a case study of using SHAP on lending data. We have tested it across multiple sort of number of examples. So the stability of Shape, like when you test it on 1,000 examples or 10,000 examples or 100,000 examples, stays the same, right? And so that's what we are using.
Thank you for the talk. Typically, models are optimizing a loss function, but they're not optimized for fairness. So how do you reconcile that?
That's a great question. So we're not we're not trying to build automatic debiasing and actually injecting fairness into the model training process. That itself is a huge research area on its own. There are people working on debiasing algorithms automatically using like regularization or other techniques to introduce introduce bias as a feature as an into the optimization function. That's again, I guess I said, like, this is more of an insights platform and an analytics platform of what's happening into AI. That could be a decision that the modeler could take. Like, I would need to actually account for fairness along with performance in the objective function. And that's not something that we are doing right now today. We can tell, as I said, we can tell you what's going on, right? Within the data set, on how your model is performing on your data set, whether that's your training data set or your live data set, or we can tell you across various different segments. And it's up to the modeler to actually take that feedback and improve the models.
One more question. So typically models, once they are into production, then there can be a lot of variation, right?
That's correct.
So from your experience, are you finding that it increases the
Yeah, absolutely. I think like model performance, unlike traditional application performance, is not constant, right? So let's say you've built a traditional application, the application would perform more or less the same way, the latency or whatnot. I mean, unless like there's huge variations in traffic or whatnot, right? But a model is subject to data that it is actually getting, right? So if the data changes, it could be whatever. It could be seasonality. It could be a new trend that has come up, right? It could be like basically the user behavior has changed in how they use the product. So the model may be underperforming than what it is deployed. So that's why if you see a lot of ML platforms have a very linear workflow, right? So you train, deploy, and predict, but there's no feedback loop. What we are trying to build is a feedback loop where you actually can see what's going on when you actually deploy these models in production, and that way you can actually figure out if you need to make new improvements and actually fix any problems that you may find. Okay, thanks for coming. We have a booth in Expo. Check out fiddler.ai. I'm happy to take more questions offline. Thanks.